Everyone, I welcome you to this session on kexec based bootloaders. We're going to talk about the relevant use cases and advantages of the same for RISC-V. Hi, I'm Upesh Sharma and I work with Red Hat. I hope you are taking good care of yourself and your family during these trying times. So let's get started. So, a bit about myself. I work with Red Hat as a part of the kernel team. This is my snap from the last in-person conference hosted at the Google office. Happy days, right? Bootloaders and Linux kernel interest me. I contribute to several upstream open source projects like Linux, EFI, and reboot bootloaders. And recently I've started working and contributing to user space utilities like kexec tools and make them file also. I also co-maintain the crash utility upstream. Okay, right. So today we are going to talk about kexec, the what and the how, and then we are going to discuss a bit about some of the existing kexec based bootloaders. Then we will touch a bit on the case for kexec based bootloaders on RISC-V. At the very end, we will discuss about some recently seen issues with kexec booting on different platforms and how we can try to avoid them. Right, so let's start. Okay, so I hope a few of you might be knowing already about kexec. So kexec is a mechanism that allows you to load and boot into another kernel. This happens from the context of the running kernel itself. So this allows you to test new or experimental kernels quickly. So for example, if you're running right now LTS kernel on your machine and you want to test the latest Linux upstream kernel, then you can easily use kexec for this purpose. The second most important point of kexec is that, and it's a very important feature, which is the fast reboot time. The fast reboot time that is provided by kexec is possible because kexec basically skips the hardware initialization that is normally done by BIOS or firmware. Now, Linux kernel provides two important syscalls, kexec load and kexec file load, to enable these features. So these syscalls can be exercised from the user space to implement kexec warm booting. Okay, there are two important kernel config options which enable the kexec functionality. So these are config kexec and config kexec file respectively. Kexec is currently supported on several architectures. For example, x86 64, PowerPC 64, both the Little Indian and the Big Indian variants, S390, S390X, that is the IBM Z series, and ARM 32-bit and ARM 64. You will notice here that I have not kept RISC-V in the above list. And why is that? Well, more on that further. Now, let's see how exactly kexec works. So it basically is a two-step process. In the kernel space, kexec file and kexec file load syscalls enable loading a new kernel into the memory. Now, whereas the reboot syscall allows rebooting into the newly loaded kernel. Notice that the parameter passed to the reboot kexec syscall is different. It's the Linux reboot command kexec. This differentiates the normal reboot from the kexec reboot case. So a normal reboot case can be, let's say, executed by means of a shutdown -r command, whereas a kexec reboot is done specifically for booting into the kexec kernel. From a user space point of view, we have user space support in terms of kexec tools. So kexec tools package actually provides us the kexec utility. So more on that in the next slide. Okay, so let's talk a bit more now about user space. What happens exactly in user space for kexec? Again, it is a two-step process. You basically use the kexec utility, which is provided by the kexec tools package, and using the -l flag, you load the desired kernel from the context of the currently running kernel. Also, you can specify the initramfs image that you want to load, and you can modify the boot arguments that you want to run the kexec kernel with. Now, in my view, the safest option is just to use the same boot args that you are presently using for the currently running kernel, just to avoid any surprises, And then you can use in the second step the -e flag with the kexec utility to boot into the new kernel. So if need be, you can also unload the loaded kernel using kexec-u. Okay, so now I'm sure you must have heard about Linux booting Linux, that is kexec based bootloaders. What are those and what exactly is available in terms of various flavors? So let's see the several open source Linux bootloaders that are already available, which actually use kexec under the hood. So I have listed a few of the popular ones below. I'm sure you might be aware of one or more of these. These are Linux boot, Petit boot, kexec boot, kboot, and several more. You can find more information about each of these using their respective home pages or wiki pages. Also, if you want, at your end, you can just write a simple shell or a batch script. You can just bundle the kexec-l and kexec-e operation or commands into it and use that particular shell script or batch script to just load a new kernel from the currently running kernel and boot into it. Now, case for having kexec based bootloader or RISC V. So this is the $1,000,000 question actually. Do we have a case for kexec based bootloader or RISC V architecture? The answer is yes. Now, let me give you an example. Just picture a AWS instance running on RISC V hardware in the coming times, and it is providing you the cloud facility. Do you want it to support the kexec based fast rebooting? The answer is a big yes, because there are existing use cases that require you to have faster reboot speed, and it is important feature, especially in terms of the cloud architecture. So where are we from a RISC V point of view? Now, we know that Nick had already posted patch sets last year, both for kernel and kexec tool utility, which still needs some rework and maybe some redesign to get them accepted upstream. Also, since I co-maintain the crash utility code upstream, I can share with you that there is a interest in seeing the RISC V architecture supported there as well, because people want to debug the root cause of a kernel crash on the RISC V architecture using the VM core file that they get, and they can use the crash utility to analyze that VM core file, and that allows them to root cause the kernel failure easily. So just look at the RISC V for next Git branch for more development features that are already available on RISC V architecture. Okay, so now the important point is, right now, does kexec work fine? Does everything work fine? Or do we have some existing issues? Now, this is the interesting part, because recently we ran into some kexec booting related issues, and I'm sharing some examples with you regarding the same. So I'm sharing an example of AWS instance here, but similar issues have been seen on other platforms as well. So we just recently came across issues with random crashes with kexec kernel booting. So I have added some snaps from the bug reports of the same seen on OpenSUSE and RHEL. So what exactly caused that? Let's see that in more detail. So what happens is, let's consider that we have some DMA capable hardware. It can be a SATA disk, it can be a PCI based NIC card, or it can be a SCSI device. Now, to handle such DMA capable hardware devices, in the kernel we have low level kernel drivers, device drivers, which are also DMA capable. So these are responsible for routing the DMA transfers all the way up to system RAM. Something like this. Now, let's consider the same case and see what happens when we do a kexec operation, kexec load and kexec execute operation along with this DMA capable driver operation. Now, let's consider that the kexec load operation happens asynchronously with the operation of the DMA capable device drivers. Now, the kexec load operation will actually cause the second kernel pages and init RAMFS to be loaded into the system RAM. So we can see here the DMA capable drivers are actually putting the DMA data into the system RAM. You can see the small red bands. And when we do a kexec-L, depending on this fragmentation already existing, the kernel pages of the second kernel or the init ramfs that you want to load, they would be loaded as segments which can be scattered across the system RAM. So what happens next? Now this is a complicated diagram, but I'll try to explain you in detail. So let's see what happens when we do a kexec reboot. So as we know, kexec reboot is basically implemented as a call from user space, which will eventually land up in kernel space, and it will call the reboot syscall. Internally, the reboot syscall will call kernel kexec function, which will eventually in the hierarchy call the device shutdown function. Now the device shutdown function will basically call the shutdown callbacks of each device so as to shut it down gracefully. Now let's consider that in our example we had 3 DMA capable drivers. Out of those, only 2 implemented the shutdown callback, and the third one, let's say the PCI NIC driver, it decided not to implement the shutdown callback. So what happens now? Now what happens is that actually it will continue to serve the DMA descriptors that are already available in the driver's DMA queue, and there is a possible chance of this DMA transfer of going up and corrupting the second kernel pages that are existing in the system RAM. So as you can see, the small little red band actually overlapped with the second kernel page that is existing in the RAMFS. So basically what this will cause is that the subsequent kexec kernel boot would actually be, it will get hang or it will crash. And then you will see something like this. So you will see that actually you are getting bug reports of kexec fast boot failing on platforms. So this may happen ever so randomly because the kexec boot might not be affected, every time. This is because the corruption on the memory contents can be completely random in nature. So what can we do to avoid this? There are some suggestions from my side. So if you are a device driver author, a module author, you can consider adding shutdown callback in your driver code. This will actually help you clean up any pending DMA transactions before we boot into the kexec kernel. On the other hand, if you are using kexec under the hood, for example, you are implementing a kexec based bootloader, always think of the shutdown related race conditions that might exist. So if, for example, you are debugging a random crash in the kexec kernel boot, always see if the underlying driver, the DMA capable driver, is implementing the shutdown function or not. Here is an example of important fix done for the AHCI driver. So Prabhakar here basically did a fix in the ATA AHCI driver, and as you can see from the little red box, it actually added the shutdown functionality. And also, as you can see from the commit log, Prabhakar mentioned that since there was no shutdown function implemented, the ATA subsystem basically remained always alive, and the DMA and interrupts can possibly corrupt the contents of the kexec kernel. Let's give you another example. So for example, let's see the example of this LPFC SCSI driver. Now, what actually the added shutdown method does here is that it will replicate most of the functionality that is already available in the remove method, so as to gracefully shut down the device and not cause any random failures while trying to boot the kexec kernel. Now, what are the next steps? Very important, because there still needs to be some work done for enabling kexec functionality fully on RISC V in upstream communities. I am currently looking into thrashing out a scheme for the same, along with porting crash utility on Fedora-based RISC V setups. Like I shared with you, there have been recently suggestions and requests to have the crash utility ported on Fedora-based RISC V setups. Any suggestions or any helping hands are most welcome. You can contact me for that. In case you are seeing kexec related failures, what I would advise you is that do report them to the kexec mailing list. I have added the mailing list here. There are several kind experts there who might be able to help you with debugging the root cause. Also, as we already saw, if there are some complex kexec related failures, they can be related to a simple case of missing shutdown callback in your DMA capable driver. So always make sure to implement those. And lastly, and most importantly, if your bootloader has very low minimal debugging capability, consider adding more debugging capabilities to it. So for example, if you have an external console exposed on your machine, consider enabling the console logs in the kexec kernel so that if you land up in some issue, you can actually share those console logs on the mailing list and try to get some help. Now, normally in my experience, I've seen that these console logs are pretty useful in debugging any potential issues with booting. Also, what I can suggest you is that if you don't have any RISC V hardware readily available, just try to use the QEMU setup. Normally on my experimental setups, I also use the Fedora RISC V QEMU setups, and you can easily download them from the Fedora project website and try to use them through the Word Builder project. Now, so with that, we come to the end of this session. I hope you had a good time listening to me, and now the floor is open for any questions you might have, and I'll be glad to answer them. Thanks a lot for your time.